Okay, number 6 is a Pulley's question. So I probably want to start by drawing the diagram for this. You could draw it on the existing question, but I'm just going to draw out a new diagram, just so I've got something a bit bigger than that one. Okay, so this is what you've been given. This is particle A and this is particle B. I'm just going to go through the question just to see what information there is that I can add to the diagram. So it says two particles A and B of mass 2m and m and 2m. So that says respectively. So A has a mass of m, so it's got a weight of mg, and B has a mass of 2m, so its weight is 2mg. Attached to a light inextensible string, that's probably important, so I'm going to highlight it. Then particle A lies on a rough horizontal table. If it's rough, that means there's friction. So this bit's rough. The string passes over a small smooth pulley fixed at the edge of the table. Particle B hangs freely below the pulley. So that's hanging freely. There's going to be no friction where B is. Coefficient of friction is mu, and the particles are released from rest. Now we're told immediately after rest the acceleration is 4/9 g. So it says, writing down separate equations for A and B, find the tension in the string immediately after they begin to move. So there's a couple more forces that I can add to the diagram. There's going to be a reaction force on A between the particle and the table. There's also going to be a tension force, and that's going to go towards the pulley on each particle. And because A is on a rough table, it experiences friction. Now this probably is going to move towards the right, so the friction is actually going this way. In addition to that, then, there's acceleration. So I want to mark that on. The acceleration on B is going down, and we're told that that's 4/9 g. And the acceleration on A is probably going towards the pulley, and that's also 4/9 g. Okay, so that's what I've got for my diagram. Next part says to find the tension. So I'm probably going to need to write down some equations of motion as it suggests. And the equations of motion is going to come from Newton's second law, F equals ma. So I can take particles A and B separately, and let's just start with A. For A, I'm going to resolve in the direction we're going to accelerate, which is to the right, and the force is going to give me T minus the friction is equal to mass. So the mass of A is m times the acceleration, which we're told is 4/9 g. If I do the same for B, the way B is accelerating is downwards. I'm going to resolve down, and that's going to give me 2mg minus T equals mass, which is 2m, times the acceleration, which is 4/9 g again. Now, in order to find the tension of the string, I need to use one or both of these equations. Well, it looks like I can just use the equation for B, because that's only got one unknown in it, as we can leave this in terms of m. So I will get T equals 2mg minus 2m times 4/9 g, which is 2mg minus 8/9 mg. So I get 10 mg over 9. So that's our answer for T, the tension. In part B, it says show that mu is 2/3. Now the thing that I know is connecting all of this with mu is this equation, which is F equals mu r. So that's going to be our equation that we need to use for this. Now, from that, in order to find mu, I need to do the friction divided by R, the reaction force. So I probably want to find out what the reaction force is first, because it's a little bit easier. The reaction force is this force up here. So I need to take particle A and I need to resolve in that direction in order to find it. So that's going to be R minus mg, and that's going to be equal to 0 because it's not accelerating vertically. So R equals mg. Okay, I found R. I now need to find the friction, and then I can find out what mu is. So in order to do that, I can come over here and use the equation that we wrote down for A before. I know what T is now, so I can sub that in. So T from the previous part is 10 mg over 9 minus the friction equals 4/9 mg. So to find the friction, then I can just rearrange that. If I rearrange that, I get the friction is 6 mg over 9. Okay, so coming back to mu now, remember mu is the friction over the reaction force, which is 6 mg over 9 divided by mg. So the mg's in this one are going to cancel, and you're going to end up with 6 over 9, which simplifies to 2/3. That's part B. In part C, it tells you when B has fallen a distance of h, it hits the ground but does not rebound, and particle A is then a distance of 1/3 h from P, and I want you to find the speed of A as it reaches P. So now it's a mention of speed. This is probably something to do with SUVAT. So I put the SUVAT equations in the top corner there, and these are from the formula book, so I'm going to give them to you. And for this, I'm probably wanting to draw another diagram for this. So let's say this is the table edge with the pulley, and now B has hit the ground. So that's A, that's B, and it's dropped a distance of h. And now A is 1/3 h from the pulley. So because it sounds like SUVAT, I'm going to write down some SUVAT quantities. And this is for when A meets P, because it says what's the speed of A as it reaches P. So if I write these down, I can think about what I need to look for. So when A meets P, it's going to travel a distance of 1/3 h. Its initial speed now is going to be something else. It's not traveling, it's not starting from rest, it's going to be something else. But when it reaches when it reaches P, we want to calculate the speed, so that's V. The acceleration is now probably different, and the time, don't know. So I'm going to need to find a few more things. Before I do that, I need to consider what happened when B did hit the ground. So I'm going to draw a new diagram. So when B does hit the ground, what happens to this string is it goes slack. So no longer do we have any tension in that string, but it's still accelerating. And the acceleration of this is actually going to be a deceleration. So it's going to start to slow down when it hits the pulley. So now I'm going to consider what happens when B hits the ground. So the displacement now is going to be h, okay? Because then B has travelled a distance from h where it was, and this is from when it was all released, so it did start at rest. So the initial speed is 0, I want to find out what's the speed with which it hit the ground. I know that it was accelerating at 4/9 g, because that's what we were given in part A. So this is initially what's happened. Time I'm not worried about, so I'll forget that. And the equation I want to choose for this one is going to be this equation here, because I've got these quantities that I'm looking at. So I work those out. I'm going to end up with v squared is 8/9 gh. So v is the square root of that. Now the speed with which B hits the ground is actually going to be the same speed that A starts travelling with at this point. Because it's one string and it's inextensible, they're moving at the same rate. So that speed is going to be this one here. Rather, it's going to be this one, your initial speed. Okay, there's one more thing I need to find before I can calculate this v, and that's the acceleration. So in order to find that acceleration, I'm going to need to consider forces again. So there's one more diagram I need to draw, and that's what are the forces acting on A once the string has gone slack. If the string's gone slack, this means that there's no tension in the string. There's weight, and there's still a frictional force. The frictional force is what we calculated in part A, or actually calculated in part B. And in order to resolve the forces, I need to use F equals ma. And I'm going to resolve in the direction that we're accelerating, so that's this way. So the forces in that direction are minus the friction, and that's equal to the mass times acceleration. The friction that I worked out before was 6/9 mg. So that gives me an acceleration of minus 6/9 g, or minus 2/3 g. Because this is a negative acceleration, that means that it's actually decelerating. Okay? So I'm now going to take that, and that's going to be my deceleration. So now I've got everything I need in order to calculate v, which is the speed of A as it reaches P. So I can finally do that. And the equation I'm going to use is actually the same one as before, which is this. So v squared equals u squared, and if I square this, I'm just going to get 8/9 gh plus 2 times the acceleration, which is this, times the displacement, which is this. So I will end up with v squared equals 4/9 gh, or finally v is 2/3 root gh if I square root. Okay, so that's the speed of A as it reaches P. There's quite a few elements to that question, which is why it's really useful to draw a few diagrams. The last part, so part D, I can just write a sentence for this. It says, state how you've used the information that the string is light. If the string is light, it means it has no mass, and it's also inextensible. So another thing we could say is that we have the same tension on particles A and B. And we've used that